morning. So, we have come to the 35th lecture of this series. We will continue with the safety regulations. We were talking about the different stability regulations followed by the different navies, which have, as I said, been adapted from the main stability regulations developed by the International Maritime Organization of the UNO. We discussed in the last class about the different adaptations to the code performed by the US Navy. They have developed the code for their own particular uses, and they have made a series of codes, a series of laws by which they make sure that the hydrostatic and stability requirements of the ships, of the US ships, are met in the sea. Now, we have more or less completed on the US some of the rules. Now, in this course we are not going very much into the details of the various rules, but we are just going over them in only the main points of them. We just go through the main points, and we overall we give a account of what are the different laws that we are that are followed. Now, the next series of the next important navy which has adapted many of these rules for the for their purposes is the UK Navy. So, we will see how some of the rules have been developed by the UK Navy. Now, the UK Navy has framed its rules according to a code which they call, that booklet is that series of code is named as NES 109. The full form, it is not that important. So, NES 109 is the the series of something like the SOLAS codes. We say that NES 109 represents the series of codes that are followed by the UK Navy. UK Navy does their stability analysis. They categorize the ships into a few classes. The primary way in which they classify the ships or the vessels are in terms of conventional and unconventional crafts. So, they call some crafts as conventional and others are unconventional. The conventional crafts are the ordinary ships that we are familiar by now. We are talking about the different types of tankers, oil tankers, bulk carriers, the other types of vessels like ore carriers or container ships, or even passenger or cruise vessels. So, these kind of vessels, the ordinary kind of vessels, or also small boats, inland water vessels, tugs, all of them come under the category of displacement, come under the category of conventional crafts. The kind of crafts for which we have developed the course so far. We have hardly talked about unconventional crafts because that is an advanced stage of naval architecture design. So, since this is a preliminary course on hydrostatics and stability, the concepts of stability, we deal with the principles of stability associated with the conventional crafts, that is the crafts like we have studied. Now, there is another set of vessels which come under a different category of unconventional crafts. These are vessels that are different from the ordinary types of crafts. One of the main type of craft is a dynamically supported craft. If you remember, I have already talked about this in about 3 classes back. We talked about the what we called as the dynamically supported craft, or DSC. These are a particular type of crafts which have some of their properties, their hydrostatic properties and their even the hydrodynamic properties different from that of the conventional crafts. So, this is one category, the dynamically supported crafts. Now, another category of ships, another category of crafts are possible. These are called multi-hull vessels. So, this is another type of vessel that is called a multi-hull vessel. A catamaran, for instance, is an example, a trimaran is an example, there are pentamarans, all those kinds of things. These are vessels which have multiple hulls. Now, we will take some look at some of the unconventional crafts. So, unconventional crafts in general, we have the multi-hull vessels and the dynamically supported crafts. Now, what do we mean by dynamically supported crafts? To last time I told you that I can give you some pictures of this. As I now even vessels which have a speed in excess of 4 times L power 4 times root L, 4 times root L WL, in fact this thing, when the velocity is greater than this, means the speed of the ship exceeds 4 times root of LWL, where LWL is the length of the water line. Now, if velocity exceeds this, then that also we categorize it as a unconventional craft. So, these are high speed, very high speed vessels. So, all these kinds of different vessels come under unconventional crafts, and the UK Navy has a series of regulations dealing with them. Similarly, a series of regulations dealing with the conventional crafts. Now, like I promised in the in few lectures back, I have some slides of what we call as hydrofoil boats. That is, I already said that we have DSC, the dynamically supported crafts. We have different types of dynamically supported crafts. One of the main types of dynamic, as I said in that last class, the two types in which the two types of are displacement Now, a dynamically supported craft can travel in two modes of it has two modes of travel, one of which is called as the displacement mode and the other is called as the Foilbone mode. Displacement mode is the mode of the vessel whereby the ship travels such that the weight of the ship is balanced by the buoyancy, the ordinary condition of a conventional craft, but remember it is not a conventional craft, but it is traveling in the mode of a conventional craft. So, in that case the displacement is equal to buoyancy and the Archimedes principle holds, and the ship moves with a constant ship moves just like an ordinary ship or like a tanker, for instance. So, that is what we call as the displacement mode of that dynamically supported craft. Now, another possibility in which the dynamically supported craft can travel is what we call as a Foilbone mode. Now, an instance for this is when the ship is not supported by the buoyancy, but the ship is supported by the lift forces from hydrofoils. So, just to mention that, you have to, I did mention there are things called foils, that is we call them as aerofoils or hydrofoils. This picture, for instance, is an example of a hydrofoil craft in which you see these things. Here you will have foils. This region you are seeing here, there will be a region in between below the water, a kind of pontoon below the water, that is actually a hydrofoil. So, this is a general picture of a hydrofoil craft. So, now how does a hydrofoil work? Now, how does a foil in turn works? Though not that important for this course, we will just mention quickly, that is this picture represents how the this is an example of a hydrofoil or a aerofoil. So, this is the shape, this is the shape of a hydrofoil. Now, this is known as a camber, this we call it as a camber, the midpoint, the midline, the camber of the hydrofoil. This we call as the thickness of the hydrofoil. So, the camber of the hydrofoil and this is the thickness of the hydrofoil. Then the angle at which the water, this is a hydrofoil, let us consider hydrofoil, and the angle at which the water enters here is known as, this angle is known as the angle of attack, alpha. Or it is actually the angle between the, okay, it is not drawn, it is the angle between the hydrofoil and the angle at which the water is hitting the hydrofoil. So, this is called as angle of attack. These are parameters upon which the lift produced by the, now the concept of a hydrofoil is this: when water flows like this, when water flows, water comes here, it will split into two, some water will go above some water will go below. Now, you will see from hydrodynamics, or you will when you are doing the calculations from hydrodynamics, the hydrofoil is designed in such a way that this part of the hydrofoil means this surface of the below this, the under the down part of the hydrofoil, this region of the hydrofoil is really will be associated with low velocity, and this region of the hydrofoil, the above part of the hydrofoil, will be associated with high velocity of the fluid. Now, therefore, when the fluid, so when there is a hydrofoil, the fluid comes from one side and it hits the hydrofoil at this edge, we call it as the leading edge, this edge, the leading edge of the hydrofoil, and this edge we call as the trailing edge of the hydrofoil. So, you have a hydrofoil here and the water comes and hits the leading edge, and the water splits into two. Some water goes above the hydrofoil, some water goes below the hydrofoil. The region that goes below the hydrofoil has a lower velocity, the one above has higher velocity, and therefore, this is a distribution over which this is the velocity distribution over the entire domain. Now, what will happen is that, in case you are not familiar already, there is a formula called Bernoullis equation. This Bernoullis equation states that the pressure and velocity in a domain, the pressure of the fluid and velocity of a fluid, of course, in case of inviscid fluids means flows without viscosity, and to a large extent the flow outside the flow far away from the surface of the body can be considered as inviscid, therefore, Bernoullis equation states that P by rho plus V square by 2, this is generally known as the Bernoullis equation over a streamline. So, the Bernoullis equation states that P by rho, where P is the pressure at that particular point, rho is the density of the fluid at that point, plus V square by 2, where V is the velocity of the fluid at that point, plus Gz, where Z is the Gz is the potential the geopotential of that point, Z is the height of that point above some datum. So, that is equal to constant over a streamline. Now, therefore, you see that from this equation directly we can see that when P increases or when V increases, the velocity of that fluid in a particular region increases, the pressure at that point tends to decrease. Similarly, when the V decreases, the pressure at that point tends to increase, because P plus V square, as you can see here, P plus V square, this whole thing, if you consider this as a constant, this plus this is a constant. So, if this increases, this decreases, this increases, this decreases, so that the sum is a constant. So, this is the Bernoullis equation, and as a result of Bernoullis equation, I have said that this is a region of low velocity and this has become a region of high velocity, and the velocity distribution, remember, has come because of the shape of the hydrofoil. The hydrofoil is designed in such a fashion that the lower region gets lower velocity and the above region gets higher velocity. So, this lower region is what we call as the pressure side of the hydrofoil. This is the pressure side, and this region is known as the suction side of the hydrofoil. This is also known as a face, and this is known as the back. Different synonyms for the same thing. This is known as so when you have a hydrofoil, you have the region above the hydrofoil. So, the region above the hydrofoil is known as the pressure side, is known as the suction side, and the region below is known as the pressure side, and this is the back, this is the face. So, what happens? We have already seen that you have higher velocity on the suction side, lower velocity on the pressure side. So, as a result of which, as a result of the Bernoullis theorem, automatically this region becomes high pressure, this region becomes low pressure. Therefore, you will see that, so if you have the hydrofoil, So, this is the pressure side and this is the suction side. So, at the pressure side you have high pressure and at the suction side you have low pressure. So, as a result of which what happens? There is always a force from a region of high pressure to a low pressure. As you know, pressure gradient is a force. So, dou P by dou x for instance is actually force per unit area, force per unit volume, sorry. So, dou P by dou x represents the force per unit volume. So, there is a force acting between this region and this region. So, from here a force acts to this side like this, a force acts. This force is known as the lift force. So, the lift force is purely due to the pressure effect. So, the pressure, high pressure on one side, low pressure on one side of the blade causes a lift through the, it causes a lift which pushes the blade up. Therefore, there is a tendency for the blade to go up. This is the concept on which the aeroplane also works. That is, when you have the aeroplane, you have the wings, you will have a aerofoil on that case, not a hydrofoil. The only difference between a aerofoil and a hydrofoil is the fluid medium in which it operates. So, in a hydrofoil, it's both are foils and one operates in the hydro mode, the other operates in the aero mode. So, one becomes a hydrofoil and the other becomes an aerofoil. So, the hydrofoil, I mean in the case of aeroplane you have a aerofoil. So, the air comes from one side, it flows in the same fashion I have described, it comes at some angle of attack and because of the pressure difference created on both sides of the wing, it lifts the wing. Remember, it lifts the wing on both sides. Now, if the lift force is enough to balance the weight of the airplane, you will see that the airplane, it is enough to hold the airplane in the air. So, at some height, if the lift equals the weight of the airplane, it remains at that height, and in cases if, and at the time of takeoff you want the lift to be greater than the weight of the aeroplane, so that it accelerates upwards, there is a net force upwards. So, it accelerates upwards, that is what happens during the. So, the lift will be, and this lift can be modulated, this lift will depend upon the pressure distribution, that can be modulated by changing the angle of attack. You will see that any aerofoil will have an angle of lift that keeps increasing with the angle of attack. If this is the angle of attack, the lift on the hydrofoil or the aerofoil will keep increasing. It will reach a maximum at about 17 degrees and then after that it will start decreasing. That is not important here, but at any rate it reaches a 17 at around 17 or 15 degrees, you will have the region of maximum lift or the maximum lift coefficient, that is something related to this lift only. It is a coefficient which parameterizes lift, the value of lift, it is a non-dimensional value of lift. So, this is the concept of lift. So, this is a process by which a hydrofoil can generate a lift. So, as you have seen in this picture, these things which are the hydrofoils here, there are hydrofoils below here, like pontoons there are some foils, it is not pontoons, it is foils. So, you have in that direction horizontal foils, these foils will generate their own lift, they will generate due to this flow, there will be a high pressure, they will generate their own lift and this lift will balance the weight, this lift will balance the weight of the ship. So, this ship's weight is balanced by the lift produced by the hydrofoil. Now, so the difference in pressure between the upper and the lower sides of the hydrofoil will give an upward force which is the lift, which will be now and that will give you per unit length, and when you integrate it over the whole length of the ship, you will get it over the whole length of the ship, the total lift force, and this total lift force will become equal to the weight of the ship. Therefore, as you see here, the weight of the ship is now not balanced by the buoyancy force, which is the according to the Archimedes principle, but the weight of the ship is now balanced by the lift force due to a hydrofoil. So, we call it as a Foilbone mode or a foil mode. So, this hydrofoil operates in the Foilbone mode, and and there are advantages, as you can see, very much smaller portion of the ship is under the water. As you can see here, the wetted surface area, we have already defined the wetted surface area, the surface area of the ship which is exposed to the water, that is called as wetted surface area. Now, wetted surface area is obviously less here, much lesser here. You will see that the direct consequence of the lower wetted surface area is that because if it were the whole thing were displaced, all this area under will be wetted surface area. So, only in this case only this much is a wetted surface area. So, because of that the net resistance or the drag on the ship will become very much less in case of a hydrofoil. So, that, but it has its own problems, and also of course, when the resistance is less, the ship can travel with much higher velocities, and therefore, hydrofoil crafts travel much faster than conventional crafts. So, these are some of the unconventional crafts. So, and of course, the other one is multi-hull vessels, which I haven't got any picture. That multi-hull vessels are simple. You will have, for example, if you have a catamaran, you will have a twin hull. There are two hulls that are under the water, they are connected, and that is a different. Now, if an intuitive person, student can easily develop the theories for a multi-hull vessel. For instance, the development of the whole theory that we have developed for a single hull vessel will now one of the problems with multi-hull vessels, as you can already guess, is one of it is what is the thing that changes very much due to the multi-hull vessels. Volume, of course, because there are two hulls, the volume under will increase. So, that is the one, wetted surface area will increase, all those things will increase. The main difference is going to be in I, which is the moment of inertia about the central line, the moment of inertia about the center, because note in this case you will be having two hulls like this, and they are connected, of course, and that is all there, connected and all that. And now, here also they will be connected, that is design. Now, these will be two hulls that are connected like this. So, this represents, for instance, a catamaran, and what we have to see here is this I. Now, what is the center line? This is no longer the center line, this does not become the center, this becomes the center, this is the center of the, like this becomes the center line of the whole vessel, the multi-hull vessel. Therefore, we take I, we will be taking I about this center will be I b LB cube of this plus A into this distance squared, LB cube of this plus A into distance square of this using the parallel axis theorem. So, this gives you the net I for the ship. Therefore, you can see that the B m, which is given as a metacentric radius, I by del will be very large for that means it will be very large, means in general you will see that B will be very low, the net center of buoyancy will be very low and metacenter will be slightly higher. Therefore, Bm will be quite larger than an ordinary ship, and G, of course, as such does not change. Gm increases because m is now slightly higher, G is as the same as for ordinary ship. So, Gm increases and therefore, the stability of the ship will increase definitely, but of course, as you can see, volume has increased, wetted surface area has increased, as a result of which the resistance drag will increase, the power requirements will increase, as a result of which more power is required to, you need higher diesel engines. If a monohull vessel requires let us say 20,000 kilowatts, a multi-hull vessel will be requiring 35,000 40,000 kilowatts. So, that much difference in the diesel engine power requirement is there. So, that much more consumption is there. So, that is a problem, but stability is more. So, these are some of the advantages and disadvantages of multi-hull vessels, and so these are the unconventional crafts that the UK Navy is talking about. Now, let us look at some of their rules. They have the conventional crafts, they have a series of rules. Some of them is that, one of them is that this thing, that is the area. So, everything about the stability of ships, conventional crafts definitely, probably not unconventional crafts so much, that is it is all about the area under the GZ curve. So, always you are going to talk about the writing moment. So, the area under the GZ curve, so area under the curve up to 30 degrees should be greater than or equal to 0.08 meter radians. Note that these are all rules for the UK Navy. There will be slight differences between the rules of the IMO, rules of the US Navy and the rules of UK Navy or German Navy. There are slight differences. Now, up to same thing, area under the curve up to 40 degrees should be greater than or equal to 0.133 meter radians. So, the dynamical stability is of course delta into GZ, but if you consider just the GZ curve, delta is just a constant, it is the weight of the ship. Now, the area under the GZ curve up to 40 degrees should be greater than or equal to 0.133 meter radians. Now, area, same thing, area of the curve between 30 and 40. So, area under the curve between 30 and 40 should be greater than or equal to 0.048 meter radians, and 3 rules. And then fourth one is that the maximum GZ should be greater than or equal to 0.3 meter. Now, always your writing moment, the maximum writing moment should be in the range of 0.3 meters. So, these are some of the, so you can see whatever be your type of ship, these are conventional crafts. We are talking about vessel, of course, we are talking about mainly vessels of larger dimensions. We are talking about 100 meter vessels or anything starting from these are all conventional crafts starting from about I believe about 30 meters up and going up to about 200-250 meters. So, these vessels they should have their maximum GZ definitely greater than 0.3 meter, and all these regulations regarding the amount of area between 0 to 30 and 40 degrees. These are some of the rules. Then they also have the UK Navy also has a series of rules regarding passenger safety for passenger vessels. Now, in case of passenger vessels, we are talking about that vessels that carry passengers only mostly. It says that always at any, if the vessel is carrying passengers, note that we talk about passengers, when we talk about passengers we are not talking about crew as such. That is a any ship vessel will have crew. We are talking about whether it be a container ship or a oil tanker, it will definitely have. So, passenger ship is a different type of vessel which is a kind of cruise ship which carries passengers, and when you have such a passenger vessel, it has some other requirements in addition to the requirements that are given for the ordinary conventional ships. These are also conventional ships, we are passenger vessels are also conventional ships. These vessels have additional rules, that is the angle of heel should always be less than 15 degree. So, you cannot heel more than 15 degree, whatever be the condition, means whatever be the wind, turning, passenger. Now, another thing that happens due to the passenger vessels is the special case when you have all the passengers crowding to one side. If it is a cruise vessel, suppose they are sightseeing, all the passengers crowding to one side, the heel, in that case also that heel is also considered. So, 3 cases: wind, turning, cargo, 4 cases, and finally, the passengers all crowding to one side. So, all these conditions will, whatever be this thing happening, it should, the angle of heel should be less than 15 degrees. Then it says that the angle of heel or the writing arm, we have already talked about what we called as the first statical stability and the second statical stability angle. In the GZ curve, we have already seen the first angle of statical stability and the second angle of statical stability. Now, in that curve, the GZ at the point of first statical stability should be less than half the GZ of the maximum. So, maximum GZ, if x is the maximum GZ, this at phi ST1, what we call as a phi, call as the statical angle at the statical stability, first statical stability angle, the GZ at that angle should be at least half of x, it should be at least be x by 2. Then your reserve of stability, we have already defined what is the reserve of stability. If you draw the GZ curve and if you draw the heeling arm curve, let us say in case of the wind heeling arm, if you draw the GZ curve and the heeling arm curve, the total area is the total area, total area under the GZ curve is one thing, and the area between the area that is outside the outside the heeling arm curve like this. So, this is the total area, and if you draw the heeling arm curve, this angle, this area, so this area is there, this whole area is what we call as the reserve stability, area of reserve, okay, it is gone outside. So, the reserve stability, so this should at least be half of the total, that is another rule associated with passenger vessels. So, three rules. Now, you will see that if you compare the two between the UK regulations and the US regulations, you will see the conclusion that the UK regulations are much more stringent than the US Navy regulations. Means the UK Navy has more stringent regulations than the US Navy, it is more strict in that sense, means the criterion are more tight. So, are lesser, means you cannot be as relaxed as in the US case, that you can see if you compare the two. And then now what we have are now we have the condition of small boats. Now, we have another type of series of vessels by the UK Navy, that is the UK Navy, the third series of first we had the conventional basic regulations, then some about passenger regulations. Now, when we consider the small boats, we are talking about boats less than 20 to 30 boats of the length of 0 to not 0 at the range of 20 meters or 25 meters, small vessels. Now, these vessels have their own series of rules. They have it says that the maximum GZ, it says that the maximum GZ for such small boats which are talking about less than 25 meters long or 24 meter load is that is LWL is approximately of the range of 24 meters. This is what we are calling as small boats, they call it a small work boat or pilot boat. They are all easily piloted. So, we have which says that the rule says that the maximum GZ should occur less than 25 degree heel. Now, when you draw, that means this should not be greater than 25, it should not be greater than 25 degrees. The maximum GZ should not occur at an angle of heel greater than 25 degrees. That is the first rule. Now, when GM effective should now the GM effective, which is known as the effective metacentric height, you know that it is a metacentric height, that is, first of all we have the basic metacentric height accounted for by hanging loads, free surface effect, transfer of loads. When you account for all that, you end up with what we call as the GM effective, and in case of such a GM effective, which is the effective metacentric height, we say the rule says that for small boats the effective metacentric height should definitely be greater than 0.35 meters. So, this is an important rule. Then there are some kind of rules for multi-hull vessels as well. So, there are rules for multi-hull vessels. Says that one, it says that if GZ, that is the maximum righting arm, is occurring close to the region of 15 degrees, then the total area under the curve, total area under the GZ curve should be greater than or equal to 0.085 meter radians. Now, you will see that in case of small work boats, we are talking about the pilot boats or the work boats of the range of 24 meters. These boats will have their maximum GZ, the maximum in the curve will occur very early, close to around 15 degrees. We have already seen that in case you have larger ships, we have already drawn the GZ curves of larger ships. There, I mean, in case you have the larger ships like a large passenger vessel or a container ship, if you draw the GZ curve, you will see that the GZ occurs mainly in larger angles. It occurs around 40 degrees or 45 degrees. The larger the ship, in general, the GZ, the position of maximum GZ moves further down the heel, it goes further down there. In case of small workboats, you end up with an angle of heel, maximum GZ occurring at an angle of heel of around 15 degrees. If that is the case, it says that the total area under the curve should be greater than or equal to 0.085 meter radians. That is the first rule. And the second rule is that, or this rule can be stated in general, that the area in general should be 0.055 plus 0.002 into 30 degrees minus 5, where GZ maximum is occurring. So, what this equation states is, this is the area, this much of area should at least be here. So, if phi max is occurring at 15 degrees, as this first rule states, if GZ max, this is GZ max. So, if GZ max, phi of GZ max, that is what it is. So, if phi of GZ max is 15 degrees, you put it here, you will get an area of 0.085 meter radians. So, this is the basic, this is the general rule for the amount of area under the curve you should have if you have a small pilot boat. And if you know the phi of GZ maximum, that is the angle of heel at which GZ maximum occurs, then you are relating the area to this. Then now the another rule says that the area phi between 30 to 40 should be greater than or equal to 0.03 meter radians. This is another rule, not phi, the area under the curve, area between. So, the rule says that the area of the GZ curve. So, when you draw the GZ curve, we have already seen, first condition holds that it should be, means we see that roughly the phi comes around 15 degrees, and provided you know what is the phi GZ maximum, which is the angle at which the heel at which the GZ is maximum, you have an expression for the area under the curve, minimum area under the curve, that much area is required for stability. Now, also in the angle between 30 and 40 degrees. So, in the region between 30 and 40 degrees, you should have 0.03. It does not have to be 40 degrees, it can also be the angle of flooding. So, the minimum angle of flooding. So, in the angle between 30 to either 40 or the angle of flooding, whichever is smaller, the area under the curve should be at least 0.03 meter radians. That is one rule. Then at 30 degrees, at phi equal to 30 degrees, the GZ should at least be equal to 0.2 meters. So, at an angle of phi equal to 30 degrees, GZ should at least be equal to 0.2 meters. So, this is very important rule. Then now, it also says that the phi of GZ maximum should roughly occur around the region of 15 degrees. It actually note that this GZ curve is actually a property of the ship. So, it has nothing really to do with the wind that is occurring or the turning, amount of turning that is happening, or the passengers on the board, or the machinery on the board, or the propulsive system, nothing. GZ curve is a property of the hull structure. It depends on the structure. That means, how it depends upon things like the block coefficient or the prismatic coefficient, different it depends upon the length, breadth, it depends on the lines plan, it depends on the hull shape. I mean, it basically depends on the hull shape. So, that is the that is what GZ curve depends on. Now, this GZ curve, therefore, it really defines whether your ship is stable or not. One quick way to look at it is, look at, for a small boat, the rule says that your phi GZ, if should be phi of GZ maximum, means the angle at which you are having the maximum GZ should be somewhere around 15 degrees. If you are talking about a ship that has a length of about 20 meters, as we have said 24 meters, this what we call as a small workboat or a small boat, a boat of this length, and if you end up with a GZ maximum occurring at a angle of heel, let us say 30 degrees, then the conclusion you can right away draw is that the ship is unstable. Something is, it's not going to work, it's going to somewhere at some point it will capsize, means it's an unstable ship, because it can be due to a wind heeling arm, it can be due to, maybe it's inherently unstable, means it just doesn't float, it's just not the proper design. That 5 of GZ maximum for such a, remember, for a small boat, but if you are talking about a large ship, your 5 GZ maximum should be somewhere around 35-40. So, these are some basic guidelines you can apply when you can just look at a ship GZ curve, and some in most of the cases, 95% of the cases, you can directly say whether the ship is, at least from the first inspection, whether the ship is okay or not. So, this is one thing. The pilot boat, if you are talking about small 25 to 30 meter boats, you should have phi somewhere around the region of 15 degrees. For large ships, phi around phi where GZ maximum is occurs around 35 to 40 degrees. So, this is some basic guidelines. So, these are some of the rules of the UK Navy, and note that you try to always to have your this another rule which we mentioned for the large ship also, for the conventional craft, for passengers also we mentioned this, the metacentric height GM effective should always be greater than 0.35 meters. That is a fundamental criterion. It is true even for the small boats. Even for the small boats, the GM effective should always be greater than 0.35 meters. GM is the, of course, in small boats there is no such thing as free surface effect, because you are not going to have tanks in a small ship, small boat. So, you can say that the metacentric height, not GM effective, just the metacentric height GM of this kind of small boats, GM should always be greater than 0.35 meters. These are some important criterion that have to be followed while studying the stability criterion. These are followed by the UK Navy. Now, similarly, similar series of regulations are available for small internal water vessels. Internal water vessels means, internal water in general means vessels that ply on water other than in the open ocean. It travels inland waters, internal waters, or its inland waters are those that travel like in lakes, small estuaries, small lagoons inside, or such small rivers. It travels in such, those kind of boats are called as internal water vessels. Now, there are a series of laws that UK Navy has regarding that also. Now, one of the main rules is that the heeling in such small vessels, heeling always does not exceed, that means it should always be less than or equal to 10 degrees. So, the heeling of such internal water vessels, that is the vessels in such lakes, should always be, heeling should be less than 10 degrees, and of course, you should have the GM should always be greater than or equal to 0.35 meters. This also holds. So, these are just some basic regulations. There are a lot of more regulations, means just by satisfying this your ship will not be classified. You have to follow a lot of other guidelines if your ship has to be classified, let us say by the Indian Register of Shipping or by the American Bureau of Shipping. They have to follow a completely different, they have to follow a lot of other guidelines as well if they have to be certified. So, these are some basic things. So, we talked about different kinds of, so we saw that the basic safety regulations have been developed by the International Maritime Organization, and they have been adapted by many people like the US Navy, the UK Navy. UK Navy in general having more stringent conditions than the US Navy, and they have their own regulations for the different types of vessels, and that is an important thing. That is, these regulations developed is not, it is not for it's not a uniform thing for all types of vessels. So, different types of vessels which are used for different types of conditions, I mean different, it has different fields of operation or the different modes of operation, their methods of operation are different, their purpose of operation are different. So, when everything is different like this, they have different series of rules pertaining to them. So, for instance, as we have seen, we have split up the rules for the UK Navy, they split up the rules for conventional, unconventional crafts, series of rules. Then they have a series of rules for the passenger vessels, then more rules for small pilot and small type boats and pilot vessels. Then then similar rules for the internal water vessels. So, like that you have then another country which follows stringent rules is a Swiss regulations. They are also important, but it's not, we are not going into it because there is not that much time and it's not that important. So, there are, these are some of the regulations. Then another series of regulations followed mostly are by the German Navy. They have a very stringent set of regulations as well. Now, these German Navy have their own series of regulations, and those regulations come under a booklet by the name of BV 1033, that is the name of the booklet which contains the German regulations for different types of vessels. Now, the German Navy first of all categorizes the vessels into different sections. They divide the vessels into different categories. So, this is how they first of all categorize the vessels. They are categorized on first category. First of all, instead of categorizing mainly on the type of craft it is, means it whether it is for a conventional or like the UK Navy does, that is one way of categorizing the crafts. German Navy follows a slightly different procedure. They categorize the crafts on the type of seas on which the ship is going to ply. So, if the ship is going to ply on winds between winds in the excess of 90 knots, we are talking about very high winds here. 90 knots is 45 meter per second. So, these are very high winds. Note that in general, even if you consider a hurricane travels at about 150 knots, probably 150 or 160 knots. So, 90 knots is very high winds, very strong winds, and when you have these kind of winds, there are some regions of the ocean which are always subject to this kind of winds. Some of the very rough areas of the world subjected to these winds, for instance North Atlantic, some regions are like that, or the Baltic Sea. Some of these regions are very always there are very exposed to such winds. So, these winds these vessels that ply under the strongest winds are called as group A vessels. Then they go about 90 knots, they go in winds of 90 knots. Then group B vessels are vessels that travel, that are exposed to winds in the range of 70 knots. Group C in the region of 50 knots. Now, when you are talking about 50 knots, we are come to some very rough regions of coast, they have 50 knots. Some of the regions of Florida coast or even the North Carolina's coast, some of these regions have stronger winds up to 50 knots, that is 25 meter per second. Then when we come to lower winds, we are talking about maybe the coasts of Bay of Bengal, for instance, or the coast of Arabian Sea. We come to winds probably about 30 knots, 20 knots or even less, that is 10 meter per second. These are strong, of course, for these regions these are strong winds, and 10 meter per second is not much these winds. So, when these winds occur like these regions, we call them as group E region of group E category of vessels. So, from A to E they have split the categories into different vessels with which sail in different types of winds. So, these are the this are, and just remember the name BV 1033, that is the so this is the that is the type of that is the name of that code. Okay. Now, Also one thing to note is different types of loading conditions. Now different types of loading conditions are important. Though not, we are not going, that is, this is how German Navy, this is again further adopted by the German Navy only. Of course, also in some form or other it is adopted by the other navies as well. We talk about the different loading conditions. First of all, you have what we call as the loading case 0 condition. This means an empty ship. Therefore, we call it an empty ship ready for operation, means everything is, the ship is ready for operation, everything is there, and that is all machineries, everything is there, and but none of the loads are there, but machinery is there, the propeller is there, the hull is there, hull is fully defined, all the structural members are there, stiffeners, bulkheads, everything is there, the deck, keel, everything is there, but and the machinery also is there, the equipments are there, but the load is not. This is called as loading case 0, it is called an empty ship. We sometimes call it as the lightweight also, and then the next we call it as loading case 1. This is with limited displacement. The meaning of this is, we are now talking about a ship which has some additional weights in addition to this machinery and all that. We have the crew, you have the crew and their personal effects. So, we have the crew and their belongings. Then we say 10%, these, remember these are all fixed rules, consumables. By consumables, anything, food and water are consumables, and anything that you use on ship, anything else is a consumable. Whatever you use in the crew uses, even the engine oil is a consumable. So, different kinds of such thing, when you, if the total capacity is 100%, so 10% of such consumables, these come under the loading case 1. Then we talk about 10% fresh water. Of course, it kind of comes under the previous category, it's previous heading, it's previous, it comes under this. Then we talk about lubricating oil, 10% of this, then lubricating oil, fuel, then we also say feed water and fresh water, drinking water. Then in case of, we are talking about a fighter ship, we also talk about weapons. Weapons are what we call as ammunitions. Now we can have 10% of everything, we call it as the loading case 1. Then finally we come to loading case 1A. Loading case 1A, this is what the German Navy calls as loading case 1A, is a case when you have the rest of the stuff, that is, you have the ammunitions, you have the full water, you have the full ballast water, fuel, lubricating oil, food or grains, whatever you have, everything is called as loading case 1A, that ends up with your loading. So, these are different kinds of loadings that are so there are a series of rules and regulations that deal with the condition of the ship at various conditions of loading, whether it is loading case 0, 1 or 1A. There are some stability requirements that are to be followed for all these 3. So, that is very important. So, this is how the whole stability requirements are done by the Navy. So, with this we can stop the stability requirements. In fact, if you really go into stability requirements, there are much more, and it is a very vast field, and what we call as maritime regulations is a vast topic in itself, it is an entire course in itself. So, we will just mention, we will stop with this series of rules. Just remember some of the rules which are very important. and know that the different categories of rules adopted by the different navies, some important things at least you should remember, keep in mind. And okay, with that we will stop today. Thank you.